Okay, welcome to CS 4510. What is this? L02A. The topic of today is something called non-determinism. Have you guys heard the word non-determinism in any other context besides this class? Maybe in a paper or something? There's a reason I asked this. No. Sometimes the term non-determinism is used in the context of a program to mean that it has some behavior that is not quote-unquote deterministic, in the sense that on the same input it doesn't always give the same output for some reason. That's sometimes people use non-determinism to mean like the behavior appears randomized, but we can't actually tell like how or why. That's not exactly the precise definition of non-determinism that we'll use, but it's maybe one you've heard before. In this class specifically, we will distinguish between randomized computation and non-deterministic computation. But today's topic is about non-determinism. So recall what we did last time. We defined these DFAs as tuples Q, sigma, Q0, delta, and F, right? And we noted that they're like weak. They're not really like very powerful. They can't really do anything. It appears, and we'll prove this later, in fact, next time, that they just kind of like do pattern matching kind of stuff, really. They're highly repetitive. They can't really solve any interesting problems. So obviously we began with a base computational model. Let's generalize it. Let's come up with another model and see if that gives any power, in the sense like maybe we can decide more problems that we think we can't do with this one. Right? So of the parts of the 5 parts of the DFA, which one really should we try to generalize? Like what part is really important? So those are some states. They kind of don't move. The alphabet doesn't really matter because like making a bigger alphabet does not appear to change any problems. In fact, the problems that we kind of really want to study are independent of specific encodings. When we write prime numbers, for example, we write 17. That's a number, but it's also a representation of a number by 2 symbols, right? So the fact that this is prime, a prime number has really, the primality of such a number has nothing to do with the representation of the number, because we could write the same number in binary. Was that 16, 8, 4, 2, 1? Those are both different sequences of symbols that represent the same object. But we're not asking a question about the object. We're asking a question about not the representation of the object, excuse me, but the object itself. So it doesn't really matter how we represent them. And a lot of problems have many different ways to represent them. So the alphabet also doesn't really matter. Changing that doesn't really change anything. Making it bigger doesn't really improve anything. Q0, I mean, we gotta start somewhere, so let's just leave that alone. Delta and F. F, you have to accept somehow, so we can just kind of leave that alone. Delta is really the only thing that matters. Delta is the only part of the computation. And recall for a DFA that it takes on a single state and a single symbol, and it outputs a single state, right? So this is perhaps limiting, maybe. We'll see. Let's try to generalize this. So let's change the function up and make it more general. Let's like generalize it. Let's give it some strength and see if that helps us do anything. So what we do now is we define an NFA to be exactly the same. But the delta, we'll talk about it in a second, is going to be a different kind of function. So what is this function going to look like? It's going to have 3 additional powers. The first one is called implicit reject. Implicit rejection is actually not particularly a very impressive power, but it's at least useful. What this means is in the DFA definition of the transition function, when you have every single possible state symbol pair must be defined. Here, we allow implicit reject because we just don't want to define things sometimes. For example, in the DFA, we could do something like this. Right? What does this DFA accept? What language does this DFA accept? The question is, I guess, what set of strings bring the DFA to the accept state?
Everything starting with A?
Yes, exactly. This is exactly the DFA that decides the language of every the only strings that bring this DFA to the accept state are those that begin with the letter A. If they begin with B, of course, they reject here. Now, if we were to do this with implicit reject, by the way, the DFA does not have implicit reject. The NFA will. But if we were to do such a thing, it would look like this. Okay? It's just simpler. Now, what is the difference here? Let's say you're at this start state. Let's call it Q0. What happens when you see a B? It's not defined. So what we do is we just say you immediately reject. You go into the garbage can. If some transition is missing, computation is just immediately thrown out, right? The only difference in implicit reject is just we don't have to write this extra state. Sometimes you manually have your implicit reject in the DFA. Here you have explicit reject, right? Here it's just ignore it, and we're good, right? This one's not particularly difficult. Questions on that? Right. The second generalization is a little more interesting. It's called epsilon transitions. Epsilon transitions, so when you think of your string, let's say like A, B, A, what happens is each letter is in some sense like a toll. It costs something off the front of your word, right? To take a transition, if this is your input, you have to use letters up off the front, right? But what if you allowed transitions to be taken, quote unquote, for free? And that's all an epsilon transition is. So suppose we had something that looks like this. What strings bring this DFA with implicit reject to accept?
It accepts strings starting with A, and then after the A it contains only B's.
Yes. So it's AB, AB, ABB, ABBB, and so on, right? Something like this. What we can do is define epsilon transitions to be something like this. So an epsilon transition is denoted by a special symbol, which is the epsilon, which is really the empty string. Now, again, the empty string is not part of the alphabet, but it is now a specially defined transition in the sense that you can take it for free. So this smaller automaton here accepts all the same strings still, AB, A, AB, ABB, and so on, but it accepts more strings. What happens here is you take the epsilon transition, and then you can take the number of B's. So by having a transition like this, two transitions in fact, one with an A and one with an empty string, the epsilon, it in fact means that you can choose whether or not you take the epsilon or not. You choose whether or not you take the A. So this will in fact accept B, BB, BBB, and so on. Why? There's a computation here. Jump here, B, 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 B. It's kind of like that game Snakes and Ladders where if you land on a specific square, you slide to another square. But here, in fact, you have the choice whether or not you slide. Some computation stays here, some computation stays here, right? And in fact, you can have certain things like this. Right? So if you have a setup like this, there are in fact if this machine has two different paths that accept the single string A, right? You go A, epsilon, or then you can go epsilon, A, and both of those will accept A in two different paths, right? And this brings us really to our third, any questions on epsilon transitions? Our third operation, we give the NFA is exactly, this is the most important one. It's called nondeterminism. So in some sense, if you think of an epsilon transition, when you take the DFA, it means sometimes that you don't need a symbol in order to take a transition. And implicit reject, you can think of that a state symbol pair can map to 0 other states. But here, nondeterminism, we allow it to map to more than one state. So, for example, let's say we're in this state, and we see an A. Where do we go?
Either state?
Either, yes. Now let's say this one is accepting. Does this fragment of an automaton accept the string A or not? Again, a conceptual question, you shouldn't know this, but just taking a poll of the audience.
I assume it's 50-50.
50-50. So we want a machine, that's a good intuition. We want a machine though to say definitively yes or definitively no. So if I force you to make a decision.
Sometimes they'll say yes, sometimes they'll say no.
Sometimes also yes, sometimes also no. But let's say we wanted it to be a decision. That is a better way to think about it. But let's say we wanted this decision. What would your intuition say?
Just go to the accepting state?
Yeah, so non-determinism is existential in the sense that an NFA accepts if there exists an accepting computation. What is an accepting computation? An accepting computation is a path in the NFA to an accept state. If there exists a path to an accept state, then the string is accepted. Now, in an NFA, there are many possible paths. You can go one way on a computation, you go another way on a computation. It's not definitive. Unlike the DFA, which is deterministic, the D in DFA is for determinism. You go here, you go here, you go here, you're done. And it's certain you landed on a single accept state or a reject state. Here, we're not sure. But we say as long as one of the paths is accepting, then we accept. Now, when does an NFA reject? When should an NFA reject?
There does not exist in accepting computation.
Exactly. There does not exist an accepting computation. I'll write it twice. Now, what is the, it exactly rejects if and only if it doesn't accept. But what's another way to characterize when it doesn't accept?
An implicit rejection?
Not quite. When does the NFA reject? Like, when does an NFA reject a word? If it doesn't accept it. But what's another way to say it doesn't accept it?
There's no paths to an accepting state.
Yes. So what I'll say is, for all computations are rejecting. So what we see here, we've given actually, non-determinism is in fact a biased power, in the sense that it's easy to accept. If an NFA accepts, it's easy to determine this. All you have to do is just find an accepting path. But how do you determine if an NFA rejects? All you have to, it's not all you have to do. What you have to do is determine that every single computation path is rejecting. So one of these is easy and one of these is hard, in the sense that you could easily convince someone that an NFA accepts a string, but it's more difficult to convince someone that an NFA rejects a string, right? One of them requires more blab. So the non-determinism is biased in this way. Let's define our transition function real quick. We have, for the DFA, if you recall, it was, we went from a single state, we're at a single symbol, and we moved to a single state. We want to generalize this for the NFA. So what is delta going to do? Well, let's define ourselves to still begin at single states, okay? Now we have the option to read a state or not read, we have the option to read a symbol. There might be an epsilon transition defined. So we can take an epsilon transition if it's available to us. So it's not the case that we always need to read a symbol, but we can also read this epsilon if there's such a transition defined, right? Now we want to move to not a single state, but a set of states. So what should the codomain of such a function be? In the DFA, recall that the codomain is just Q, because in the DFA, on a state symbol pair, you move to a single state. But in the NFA, we want to move to a set of states. So what should the codomain be of the NFA's transition function? Yes. The set of states is an answer in the output. So the codomain would be the set of states, which would be what? Almost. The class of states. Classes, as we'll see later in the class, is actually a technical term. It's 2050.
All subsets of states?
Yeah. What's the name of that?
I forgot.
Not quite. I'll tell you guys. It's the power set.
Power
I
set.
think you guys just didn't remember the name of it, but I think you guys visualized it. Yeah. Okay. That's the transition function of the NFA, and it is slightly more complicated, but that is the transition function. Okay. Yeah. So how does the NFA actually, like, this doesn't make any sense, okay? Like, we're all determinism brained. What does it mean for non-deterministic computation to be there? It doesn't really. So there are we are deterministic people, okay? We can't go into two states simultaneously. So we need what are called deterministic coping strategies. Okay, so the first one is an algorithmic view. Let's say you're in algorithms class. I gave you an NFA and I gave you a word, and I want you to determine if the NFA accepts the word. What would you do to determine if the NFA accepts the word?
Just try everything until you don't.
Sure, but what's the name of the algorithm?
Well, that should be depth first search.
Yeah, in fact, BFS would also work just fine. DFS or BFS. Any kind of graph traversal would work, right? Now, what's the difference between these two? The DFS or BFS is something we have to do, but it's not something the NFA has to do. The NFA takes, and the difference is exactly this. DFS or BFS will take us more time to figure out if the NFA accepts, but the NFA still accepts without having to do DFS or BFS. It does somehow compute on the word in exactly n steps. It doesn't take any backtracking or anything. Because we would count, when we do backtracking and so on the NFA, we count that as part of our runtime, so to speak. So for us to determine if an NFA accepts takes longer than the NFA to determine if the NFA accepts. Now again, the NFA isn't real. It's a theoretical model of computation. You can't like build an NFA in your garage out of pulleys and levers. But we're just studying this model that has this supposed different kind of stopwatch for how it measures time. The second one is called the lucky coin. The lucky coin analogy is you come to the fork in the road, and what do? You flip a coin, and it tells you which path to take. It tells you, you can just guess correctly, is the accept state going to be on the above branch or the below branch? And then you follow the coin. Now, this isn't like my analogy or anything. This is part of the literature. Maybe you've heard this one before. But you just guess, and then you're there. Perhaps not very helpful, but just imagine that at each level, every time you must make a decision, you have a coin with probability 1 that tells you the right answer, and then you just follow along. And you're like, oh wow, I reached the accept state, because you were always destined to reach the accept state, right? 3 is sort of science fiction alternate timelines. Alternate timelines. So every different piece of science fiction has a different amount of fake science about how time travel is supposed to work, right? Or when you split the timeline into separate decisions. But suppose that you're in something and then you like fragment the timelines into something like this, right? And somehow these universes are running in parallel where like the first branch is if you did something and the second branch is like if you didn't do something. Now in each of those branches, of course, the computation can then again fragment and so on. This is another way to think about non-determinism. Each of these timelines runs in parallel universes, like in parallel. And then what happens is if one of the timelines has the goal that you want. You find the little coin or the something. You push a button on your magic Rick and Morty device, and you just crush the non-accepting timelines. Like those never mattered, so to speak. As long as one of your copies finds the thing you were looking for, then it accepts. So in some sense, you always find the thing this way, whatever it happens to be that you're looking for. Have you guys seen that episode of Community with the alternate timelines? You guys know what I'm talking about? Community's old now, right? Basically what happens is they roll a die to figure out who has to go get the pizza. And then they reshoot the scene 6 times, and then a 7th time, depending on who gets the die. So they reshoot the same scene with one person missing each time. And that's kind of like the same thing. Most of them end in a horrible disaster, except one of the things. This is, again, just a coping mechanism. There's no time travel, it's not real. But this is kind of the way you can think about computation on the NFA. Abstract yourself from deterministic thinking. Questions on these 3 strategies at all? Okay, let me give you some NFAs then, right? So let's suppose we want to compute the language W's in sigma star such that W ends with AAA, right? So here's what we're gonna do. First off, we want to see AAA and then reach an accept state, right? Let's call this Q0, Q1, Q2, and Q3, okay? There's a way to do this with a DFA. This specific one happens to be done with a DFA. But what you do is you would every time you saw an A, you would advance 3 states, but if you ever saw a B, you would backtrack, right? But suppose we just have this fragment of an NFA right now. Certainly, if you're at Q0 and you see A, you will hit the end, right? You'll accept. But you'll only accept if you're exactly 3 away from the end. So how does the NFA know to start taking these transitions to go there? What we're gonna do is we're gonna say, just non-deterministically guess the prefix of the string, and then when you're exactly 3 from the end, you start taking the chain of transitions that'll lead you to Q3. Now, why is this non-deterministic? Because delta of Q0A, besides the fact that it is implicit reject, delta of Q0A would be the set Q0 and Q1, right? Because upon reading an A, you could go to Q1, or you could stay in Q0. So you have the non-deterministic choice of those. Let's consider the computation of such a, there are many computations of a string on this NFA. Let's consider this one, A, right? Okay. Let's consider this word AAAA. First off, should this word be accepted by the NFA? Okay, it should be in the language. Let this line represent when you stop taking the Q0 and you non-deterministically choose to go to Q1. If you don't ever take the Q0 transition and you choose to go to Q1 immediately, what will the computation look like? You'll go A, and then what should happen after Q3? You have one more A left to read in the input, but what should happen?
It's rejected, I think.
Yes, you will implicitly reject from Q3. The input must be completed in reading. You cannot when I'm at the accept state, then I'm just gonna stay here. As long as you have input left to read, computation must proceed. Now what about here? Let's suppose you take the Q0 loop exactly once. Q0, then you go A. Well, we're on the accept state, so that accepts. Let's suppose we guess too late. Here we guess too early, here we guess just right, here let's guess too late. We go A. Q2 is not accepting though. So we're gonna just say reject on Q2, right? Let's suppose we guess even later. A, 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 A. That's gonna be reject on Q1. And let's say we guessed way, way, way too late. A, 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 A. We're gonna reject on Q0. Okay, so we see that on this specific word, there are 5 computations. And in fact, there could be an explosive number of computations, right? Imagine if a binary tree has depth k, depth n, then there are 2 to the n possible leaves. So in some sense, you get a 2 to the n possible, if you had an NFA that looks kind of like a binary tree, you could have 2 to the n possible paths to keep track of for a word of length n. Something like this. So it can explode very quickly. But this NFA accepts the word. Why? Because there exists a computation path. So it accepts. One of them accepts, we accept. Now, it should reject any word of the form AB, right? No matter how you take that word. You could go AB, reject. You can go AB, reject. Either one is going to always reject. So non-deterministically guessing the correct accepted strings is usually easy in designing an NFA, but what can be difficult sometimes is to make sure that you also explicitly or implicitly reject all the strings that are not supposed to be accepted. Like you still take care of everything, you know. Right, any questions on this example? Let's do a few more. So suppose we did 1 to the an plus b for n is a natural number. Okay. Now what this is a unary language. What this means is it only contains strings of length 1. And this has some fixed a comma b, right? Suppose a and b are like 3 and 4, or something like this, right? We have some fixed number here, and we take n a certain number of times. It's a unary language, and what that means is it only contains ones. So there are no strings with 0 in this language at all. And the length of the string is simply defined by this linear equation, right? And there's no real numbers here, this is a natural number, including 0. So the way we're going to construct this NFA is, again, we kind of need to make a non-deterministic choice here. We're going to, and if there is actually, for this specific one, a way to do this deterministically as well. I'll leave that to you as an exercise, but for now, let's just kind of figure out the way to non-deterministically do it. So let's suppose I just wanted exactly the string of 1 to the b, or a constant b. How would I do that? No other string should be accepted, I just wanted 1 to the b for a fixed b. Let's say 1 to the 7.
You have a single path of length b.
Yeah. Now, how many states will that take?
B plus 1.
Yeah, because you're counting the transitions and not the states. It's the in-betweens, 1, 2, blah, 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 b. But it takes b plus 1 states for that. Okay, so we have the 1 to the b part. How do we do let's just separately do the 1 to the an part for n is a natural number, for any n, right? How can we do such a thing? Actually, I'll ask you a simpler question. How can we do 1 to the n for any n? So this is not going to accept a single string. It's going to accept infinitely many strings. How can you accept a string only of ones? Of any number of ones?
Like the start state, just go back to itself.
Okay, easy. What if I ask for 1 to the 2n?
A loop of links to, the start state is accepting.
Oh, yes, it should be accepting as well. Right? So a loop. Could you do a to the n the same way for some constant a? So all we're going to do is put that loop of size a to the n on this NFA. I'll talk about where I put it in just a second. I put it at the start state for an interesting reason. Essentially, a computation on this NFA, hello, 4510?
Sorry?
4510?
Yep.
Excellent, excellent. A computation on this NFA is going to go through this loop. It's going to go how many times? Well, also, before we get to that, also these are all one transitions, right? It's okay we don't have zero transitions because we have implicit reject. If we ever see a zero, just throw it away immediately. Why is this non-deterministic?
Well, you can go both ways at the start state, right?
Yeah, here you have two options. You can go here or here when you see a 1, right? So what does that really correspond to, though? When you're in this loop, though, you can't go back here. You have to, like, finish the loop if you want to compute anything more, right? So what the non-determinism corresponds to is non-deterministically choose how many times you take the loop. Non-deterministically choose n, and then you just have b left over. So you go 1, 2, 3, 4, and then you take b. That 4, the number of times you take the loop is exactly the n. So in some sense, you can non-deterministically guess the n, and then make sure your a and b are set up appropriately. And this is going to decide the language, right? It also happens that there is a way to do this deterministically. It takes a little bit more programming. Questions on this example? Okay. Let's do one more. Let's do another unary one. 1 to the n, such that n is congruent to 2. N is congruent to, let's say, 1 mod 2. Or n is congruent to 2 mod 3. Right. So we have such a language. First off, it's unary. So we need, and again, I'm being explicit. I'm talking you through the programming process so we know like what's missing or what's not missing and so on. We have an or here. So we need to either ensure that n is congruent to 1 mod 2 or 2 mod 3. So we need to either check if n is congruent. Let's just solve these in parts first, right? Let's say we want to determine if n is congruent to 1 mod 2. And this is the exponent. What that really means, if it's congruent to 1 mod 2, what do you know about n in general? Yes?
Would it have to be an odd number?
Yes, it's an odd number. So let's forget this case for now. If n is congruent to 1 mod 2, it's odd, right? So let's first consider the part where it's an odd number of 1s. What's the NFA look like if it's an odd number of 1s? Yes.
Sorry, what does the what look like?
The NFA.
What is that?
Sorry, that's what we talked about.
I'm sorry.
Sorry. Well, I'll catch you up in the break.
Yes, sir.
Yeah.
Well, it's gonna be a oscillator, right? It's gonna be a loop of links 2, and then accepting is gonna be the right one.
That keeps track of mod 2. Then the accept states keep track of it 0 or 1, right? If you've seen an even number of 1s, you're here. If you've seen an odd number of 1s, you're here. Okay. Now, how do we do congruent to 2 mod 3?
You're gonna have 3 states. Right, and it's gonna be a loop also, and then, right, and you put the accepting on the second one, so it's 0, 1, 2, yeah, that one.
Okay. Now, we have 2 NFAs for 2 problems. How do we determine the language that 1 to the n if n is either supposed to be congruent to 1 mod 2 or congruent to 2 mod 3?
We use like the joining thing we learned from the last lecture.
Yeah, basically. Oh, actually, no, that would work. So if this was a DFA, these are NFAs though.
Yeah.
So we would have to make DFAs for those problems with some zero transitions and so on. They would be much uglier. We would take the Cartesian product and then we would do the union, and that would work out perfectly, actually. But that would give us a couple too many states,
Yeah.
right?
So for this one, I think it's possible to have 6 state, right?
Yes.
Right. And then it visit each, and then and then
So the DFA, let's suppose this was n congruent to, let's say, x mod A, and then n is congruent to, let's say, y mod B, right? The DFA for this would be size A times B, right?
yes.
I claim that the NFA for this is A plus B plus 1. Now, when it's 6, in fact, those are equal. So this is not a very good example. Actually, I'll rewrite that here. I don't think it can show on the video. But
I think I know what you're trying to get at.
so the NFA is smaller, certainly, for some specific NFA. The answer I'm looking for, again, is in the spirit of non-determinism, which is something I think we got to get in the habit of, because it's a superpower. We get all this cool stuff, but we've done deterministic programming our whole life. The answer is you just non-deterministically guess which NFA you're going to run it on. So what you do, you add a new start state, and then you epsilon transition to both of those. So consider the computation. You begin at the start state. You guess, do you go up or do you go down? Once you're there, you're stuck there. You can't ever get out. But essentially, your first decision made is a non-deterministic choice of whether or not you're going to try to determine if it is 1 mod 2 or if it's either mod 2 or mod 3. After you make that choice, then you check that to be true. Now, it's possible for a computation path to both be true. Is there a number that's congruent to 1 mod 2 and 2 mod 3? Actually, here's a pop quiz. Why must there exist a number that's congruent to 1 mod 2 and 2 mod 3? Does anyone remember this from discrete? I don't think you should. Suppose that OR was an AND. There actually is such a solution to a number.
I forget what you call it. but
Chinese remainder theorem.
Both of them are prime.
Euclidean algorithm?
They must be pairwise coprime, and it is the Chinese remainder theorem. You solve a system of inequalities. I don't think anyone should remember that. But basically, there must exist some number that's accepted by both. But how do we reconcile that? That's okay. An NFA can have multiple accepting computation paths, as long as one of them is accepting. So there is certainly some string, and someone find a number for me that accepts it with 2 different paths. What number is congruent to 1 mod 2 and 2 mod 3?
5.
5, yeah. So if we consider 5, we go 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5, and then we go 1, 2, 3, 4, 5. So 1 to the 5 actually has 2 different accepting computations, right? And so are multiples of it, mod 6. But that's okay. We just want one accepting computation, right? Questions on this specific construction of an NFA. And these examples we're doing are not like interesting or anything. They're just simply to demonstrate how you can use non-determinism. Like, this is something that will benefit you, that'll help you. Questions? Okay, let's do our last little, come on, technology, please. Okay, so this is a poem by Robert Frost. One of the poems of all time, I guess you could say. 2 roads diverged in a yellow wood, and sorry I could not travel both, and be one traveler long I stood, and looked down one as far as I could, to where it bent in the undergrowth, then took the other just as fair, and having perhaps the better claim, because it was grassy and wanted wear, though as for that the passing there had worn them really about the same. And both that morning equally lay, in leaves no step had trodden black. Oh, I kept the first for another day. Yet knowing how way leads on to way, I doubted if I should ever come back. I shall be telling this with a sigh. Some were ages and ages hence. Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. So, you guys had to read this poem in high school? Okay. Well, it's short, it's memorable. Basically, the moral is you have Robert Frost, okay? He's a guy, he comes to a fork in the road. There's Robert Frost. And one of them is like scary and something, and the other one is like nice and has like flowers and whatever, right? So he comes to the fork in the road and he's forced to make a decision about one that is well-traveled and one that's like spooky and maybe I should go over there, it's tempting. But the moral of the poem in the context of the class is not anything about Robert Frost, but the fact that Robert Frost is in fact deterministic. So Robert Frost is in fact forced to make a choice about which path to go. Now, suppose we had a non-deterministic Robert Frost, what he could do is he could come to the fork in the road and simply take it. And at the end of the discussion, there wouldn't be any interesting poem for it to write about because he would have both. He would have taken both paths simultaneously. In fact. So, any more questions? NFAs? All right, let's take a break.